Alright, so let's talk about Sukuna. If you've seen Jujutsu Kaisen, you know exactly what I'm talking about. That raw, terrifying power. His attacks are just insane. They slice through buildings, people, everything, like it's nothing. And on the surface, it's pure magic, right? But what if it's not? That's what we're going to dig into today. We're going to ask a kind of crazy question. Is there real physics behind this seemingly impossible curse technique?
You know, the best clue actually comes from the fan community. Someone pointed this out, and it's brilliant. The theory goes that Sukuna isn't just cutting things, not like with a sword. His technique is right there in the name: dismantle and cleave. So think about it. He's not making a blade. He's making things, well, just come apart. He's literally deconstructing them.
So that's the big question, right? What does it actually mean to dismantle something at a physics level? Can we take this idea from the anime and find anything like it in our world, in real science? Is there a way to make something just separate on its own? And believe it or not, the answer is yeah, absolutely.
Okay, so to figure this out, we're going to take a little detour. We're leaving the world of cursed energy for a minute and heading straight into heavy industry. Yep, you heard me, because it turns out engineers have figured out some wild ways to deconstruct the toughest stuff on the planet. So check this out. We've got two real-world methods for doing basically the same thing. First up, you've got adiabatic shearing. Now this is all about insane speed. We're talking about deforming something so fast in microseconds that the heat from all that bending and friction has literally nowhere to go. It gets trapped, creates these super hot spots, and the material just fails. It tears itself apart from the inside. Then you've got water jet machining. This is just as cool. It's a jet of water shot out at up to Mach 3 that acts like a saw made of pure force, just blasting material away. So here's the key takeaway. Neither of these methods uses a sharp edge. It's not about being sharp. It's about overwhelming the material. You just dump a ton of focused energy into one tiny spot super fast, and the material just gives up. It can't hold itself together anymore. And that is our real-world blueprint for Sukuna's dismantle. A raw, brute force attack that just deconstructs anything it hits.
But wait, that's only half the story, right? Because that's dismantle. What about cleave? That's the smart one, the one that adjusts to whatever it's hitting. This isn't about brute force anymore. This is about precision. It's about finding a weak point and exploiting it. Welcome to the science of structural flaws.
And the scientific principle behind this is called stress concentration. It's a huge deal in engineering. Basically, it means that stress, like the force trying to pull something apart, is never spread out perfectly evenly. It's kind of lazy. It takes shortcuts, and it loves to pile up and get way stronger around any little imperfection, like a hole or a notch, or even just a sharp corner. Turns out, everything has weak points.
And this is the perfect example of why shape is everything. Just look at the two designs. On the left, you've got a sharp corner. See how the stress gets all jammed up trying to make that turn? It creates this massive pressure point, just waiting to break. But on the right, with that nice rounded corner, the stress just flows smoothly around it, no big deal. The load is spread out nice and even. This, right here, is why airplane windows are oval and not square. It's literally a life or death design choice.
And we can actually put a number on this. It's called the stress concentration factor. Let's take a simple example. You have a flat plate and you drill a hole in it. The stress right at the edge of that hole isn't just a little higher. It's 3 times stronger than anywhere else on the plate. That hole isn't just a hole. It's a force multiplier for whatever's trying to break it.
And look, this isn't just some abstract textbook stuff. Getting this wrong has caused some absolutely catastrophic disasters. Remember Aloha Airlines Flight 243? The roof just peeled off mid-flight. Why? Because tiny little cracks started at the rivet holes, classic stress concentration points. The I-35W bridge in Minneapolis collapsed because of a design flaw in some metal plates that created massive stress points. And the first commercial jets, the Comets, they literally just fell apart in the sky, all because of stress building up at the sharp corners of their square windows. It's that critical.
Okay, so we get it. A failure starts at a weak point. But how does a tiny little crack turn into, a full-on slice through an entire building? How does it spread? Well, this next part is going to explain that automatic separation idea from the fan theories, and honestly, the physics here is super cool. All right, look closely at this. A crack isn't just an empty space. The real action is happening right at the very tip. That single point is under an unbelievable amount of stress. I mean, all the force trying to tear the object apart gets focused right there.
It's so intense, you can basically think of it as a tiny little spot where the material is literally changing phase, going from one solid thing to two separate things.
And here's where it gets crazy. This thing feeds itself. It becomes a chain reaction. So all that stress focuses on the atomic bonds right at the tip. They snap. The second they break, all that stored up energy in the material gets released, and bam, it shoves the crack forward to the next set of atoms. Then the process just repeats. The stress focuses, bonds break, energy is released, crack moves forward, over and over. It's like a wave of destruction propagating through the material at insane speeds.
So, let's pull all these threads together. We've got our 3 big ideas: brute force deconstruction, finding the weak points with stress concentration, and how a crack spreads like a wave. Now, let's use all of that to finally deconstruct the king of curses himself.
And here it is, all laid out. It just fits perfectly, doesn't it? Dismantle, his go-to slash, that's our brute force energy dump. Like that industrial cutting, it just overwhelms whatever it hits. Then you have cleave, the smart attack. That's pure stress concentration. It doesn't have to be stronger, it just has to be smarter, hitting the target's built-in weak spots to multiply its own power. And the cut itself, the way it just appears and zips through something, that's crack propagation, a self-sustaining wave of breaking bonds.
Which brings us to the final boss of this whole thing, the world dismantle. The slash that cuts, well, everything. Not just a person, but the space they're in, the world itself. So, how on earth does our physics model explain that?
And here it is. This is the big aha moment. A world-cutting attack doesn't need infinite power to slice through every single atom. No way. It just needs perfect application. Think about it. It's a dismantle where the target isn't an object but existence itself. And it's a cleave that targets the millions upon millions of microscopic, inherent weak points, the stress concentrations that exist in the very fabric of everything. He's not cutting the world. He's telling the world where to break along the seams it already has.
So let's just run through it one last time. Dismantle is basically industrial-grade, high-speed cutting. Cleave is the smart bomb, targeting those natural weak points. The cut itself is a chain reaction, a propagating wave of fracture. And maybe the biggest takeaway of all is this. What if Sukuna's magic isn't breaking the laws of physics? What if it's just mastering them to a degree that is completely, impossibly perfect to us?
And I guess that's the thought I want to leave you with. If we can apply real-world physics to something as insane as Sukuna's slash, it really makes you think, doesn't it? What other magic out there in all the stories we love is just science we don't understand yet?